complex mathematical problems. And they claim that they improve complex matrix complex multiplication from 49 scalar multiplication, reduce one operation to 48 scalar uh, multiplication. So this is an improvement for this is a problem, and people use 56 years to reduce the operation from 49 to 48. And the second is also recent news that the IMO organization claimed that the Google DeepMind, the model, the Generative series model, win the champion of the IMO, 35 score out of the 42. So also a significant improvement. And the claim is of this model is that in 2024, the level of the model is the silver level model. And the authors use AlphaGeometry 2 and another model. And this year, we only use the natural language as input, train the model, and solve the problem. So this is a significant improvement. And these are about science discovery. And we have to say that AI is now significantly changing the research and reshaping our daily lives. Let's still see some examples. And I think most of you are the first time to Harbin this year. And it is also the first time for me. So before coming here, I just chat with the model and asked the model to design a 2-hour visit plan for me. And after design, I want the model to draw a flow chart for me, tell me how to travel the city. And after 1 or 2 minutes, I obtain a picture like this, and it is generally fine. Secondly, when we do the research, especially for me, I'm switching from AI to AI for science. So many domains are new to me. And before the talk today, I want to do some related research about surveying how the large language model and generative AI are applied in scientific discovery. So I just organize my words and input them into the Gemini, the deep search mode, and ask the model to generate a survey for me and roughly generate something like this. And this can be a reading material for me to switch into this direction. And also for some more professional question like TB is a disease usually related to the lung. And the target protein is some protein that related to a specific disease. So I asked the model to summarize a table for me, tell me the potential target proteins of the tuberculosis, and summarize all the results in the table, and highlighting the difficulty of targeting this drug. And the model can indeed output something like this. And after confirming with the experts, and generally fine for me. Finally, also the strong large language model is a strong code generator or the copilot. And when I asked the model to write a code for me to calculate the number of the fused rings in the molecule. This is a simplified version of the command. And because at first I do not know how to describe my requirements in how to describe my requirement clearly. And after chatting with the model tells me that helps me summarize the problem and generate the code for me. The problem is to count the fused number, and the fused ring is defined that if 2 rings share a common edge, then we can call them the fused ring. So the answer of this question should be 5 in this case, because in the right part, there are 5 rings fused together, and in the left part, 2 rings fused together. Ask model to generate something, and I get the code like that. The method itself is not hard in terms of calculating the fused ring, but maybe the Python package RDKit is not quite new for me, especially when I start the research. So the model can help me save lots of time on using this package. And recently, the agent is very popular. So for the scientific discovery, the agent also plays a very significant role in the science discovery. And 2 work, including the AI co-scientist And the BioMini, this is a recent work. The left work is the early this year, and the BioMini is published just about 1 or 2 months ago. And for the first part, for the left part, and we want to design some co-scientists that can help us propose some hypothesis, propose some validation method, which drug I should verify, which should not, and what is the next step. And the researcher, I think the researcher sent different prompts to different Gemini. So they have different roles. One could be proposal, one could challenge, one could review, and something else. They work together to solve the problem that people propose. And by the end, they really find something useful for 2 or 3 cases. And they find some drug repurposing drug that can be used for the leukemia, and also find some potential target for the liver fibrosis. For the left part, the model from the structure, the model is similar to the left one, but the right one is more like a tool calling agent, where there are some centralized agent calling some domain-specific tools to solve the problem. And the left model is used for the biological discovery. Okay, so these are some background of the recent advantage of the large language model in scientific discovery. Next, we can briefly go through that some basic knowledge. And a key success of the previous results are the large language model, especially the GPT-based foundation models. They are very helpful to improve the research of the previous discovery. And the key principle of the GPT model is the autoregressive modeling. And the rule is very simple, just the joint probability of the PX, where the X could be a sentence and it has n words and it can be decomposed in this way. I think you are very familiar with this formula. And the concept is not new. They are proposed early 2010, I think this year. And first, people use the RN to model this formula, the RN-based language model, and the input is the input including the previous token and predict the probability of the next token. And the network architecture is the recurrent neural network. And later, about 2017, and some researchers from Meta also proposed to use CNN to solve this problem. And using CNN for the natural language processing is not a novel task, but researchers successfully applied this task to the language modeling and get some new results, I think. And after that, the transformer comes. And we have the transformer here. So basically, we have the transformer-based large language model, the GPT model. And the performance keep increasing due to the advanced technique, including both the network architecture and the use of the data. After that, we have the GPT model and the scaling law. Actually, the first version of the GPT model, GPT-1, appears about 2017. Not quite start from the 2017, and just after the proposal of the transformer model. And at the first time, the GPT model is not as strong as the BERT model. I think you are very familiar with the BERT model on several downstream tasks, especially the natural language understanding task. The performance is not as good as the BERT model. But the researcher keep increasing the model size and adding more data and improving the model from both the architecture and efficiency. And then we have the GPT-2, 1.5 billion parameters trained on more data. And yes, for GPT-2, they also claim that the GPT-2 can do many zero-shot tasks, which means that trained on several tasks and directly apply the model to a new task and obtain some promising results. After 1 or 2 years, GPT-3 comes with much bigger parameter, 175 billion parameters, and about 300 billion tokens. For this model, the few-shot ability of GPT appears, which means that we can prompt the model with several examples, and the model can mimic the behavior of the data we input to the model. And it's indeed a surprising moment, but people still do not have a clear roadmap about how we can further leverage the model. Until the GPT-4 and the later model comes, then the claim that we in some way reach to the artificial general intelligence, which means that we can chat with the model and solve almost all the tasks, especially the natural language processing tasks we are interested in. And the keywords, the scaling law appears from that time. I think that the scaling law does not refer to using a larger model, train bigger and bigger model. But it should be that the scaling law should be by increasing the number of the parameters, the size of the training data, and the computational resources, we can achieve continuous and predictable improvements in the model's performance. This is the meaning of scaling law, which means that we can train on smaller size of the model and predict when we want to train larger model, how many resources, how many data we should use. And until this moment, I think the basic objective function can be described using this rule, the next token prediction. But this is not the overall picture of the large language model. From that, people also start research of trying a new training objective function. The work starts with the instruct GPT model. And the motivation of the instruct GPT is that large language model is good, but they cannot generate some untruthful or toxic or so many hallucination. And we want to improve this phenomenon. And the idea of the instructor GPT is that we not solely rely on the next token prediction. Instead, we should also have a reward model and let the reward model to guide the training of the GPT model. To get the reward model, and the people first can have some preference on the data. We have 4 answers, A, B, C, D, which I prefer, which I do not prefer. And based on the preference data, we train a reward model on them, and then using the reward model to guide the training of the GPT. And the method used in this paper is the PPO. And based on the evaluation, the author claimed that after using the reward model, the reinforcement learning, a 1.3 billion parameter version of the model outperforms the original 175 billion GPT-3, demonstrating the effectiveness of this method. And later, we have more and more related work come from here. And the keywords are reasoning. I think you are familiar with this keyword, reasoning. And I just checked the talk list. I believe that we have the related talk during these days. So we just briefly mention something here. And this work here is the process, is the PRM, the process the supervisor reward model. And the reward model used in the previous page. And we only, for the reward model in this page, it only output the answer at the final step. But when we solve a problem, we have the step-by-step thinking. We can give each step a signal, whether this step is correct, wrong, or neutral. So we can treat a reward model like that. The input is the question, related information, and the current step. And we can make a prediction whether the current step is correct, wrong, or neutral. Based on this, we can continue the training and the inference. So this is the result from the paper. And they also claim that by using the processed supervision, it outperforms the ORM, which means that we only assign a reward signal at the end of the problem. And we also have some related methods like the direct preference optimization. And the claim is that the RHF, the previous method of the RHF, often complex and very unstable. can we just directly using the user preference? Like I have the preference data and train the model in the right part, like I prefer this one, not that one. So this is the basic idea. Based on this and some mathematical derivation, we can have the loss function in the bottom part. And we have the YWYL. We can regard W as winner and L as loser. So we prefer the answer YW to YL. And we want to maximize the gap between YL and YW and YL. Want to maximize their probabilistic gap. So we can have the formula like that and can continue. I am not a reinforcement learning researcher, but I consult the related people from my organization. And they have an opinion that recently the online reinforcement learning generally outperforms the on-policy reinforcement learning outperforms the off-policy. So we also have the online BPO version, which means that the answers are sampled online, not just sample everything offline. And later we also have the GRPO. This is an online method, and basically how to interpret GRPO. So it is very simple. It is a variant of the PPO. And what we change from the PPO, one is the reward function. Previously, in the previous slides, the reward function are generally trained or labeled by human. But here, the reward function are defined by the following two keywords. One is the accuracy, and the other is the format. For the format, we ask the model to generate the answer following our format. In this case, we should have a think step and an answer step, and the answer should be in the brackets of the answer. So we can constrain the output in this way, and we can set specific prompt for this purpose. And the other is the accuracy. We can use accuracy to check whether the answer is good or not. So this is a change of the reward function. And the other thing is that how to estimate the advantage function. We sample multiple answers from the policy, calculate the average, and calculate their mean value, and using the RI plus the mean value divided by the standard deviation, get a normalized version of the advantage like this, and use it to guide the training of the whole process. So this is the basic idea of the GRPO, widely used in today's RL research. And at the first time, in the DeepSeek R1 paper, we also claimed that this is an improvement compared to the previous method. And we met the aha moment in this paper. And also they claim we even do not need a semi-supervised fine-tuning, and we can just using the RL in this framework. Well, but according to the discussion from our side, I think basically the DeepSeek V3, the base model is super strong. So we can try many advantage technique from this part. And a strong base model is also a fundamental reason to train to develop a success method. And after we have the reasoning model according to the matrix from this website, and this is a benchmark. This is an index covering the 7 widely used benchmark. And we can divide the model as the reasoning model or the non-reasoning model. The reasoning model means that it can output the answer step by step with a thinking step. And we can see that the purple part is the reasoning model, while the blue part is the non-reasoning model. Generally, from this sense, we can see that by using reasoning, we can achieve some improvement compared to the non-reasoning model, and the improvement is non-trivial. And for reasoning also come across the talk. Well, the point from the speaker is that the pattern is all you need. Once you can design a very proper pattern to get the answer, you can design a good reward signal like that, and we can leverage that for the model training. And by the way, before going into the science part, I think we need to briefly mention the BERT model. And compared to the next token prediction, the BERT model is more like mask language modeling, where after inputting a sequence, we randomly mask several tokens and ask the model to recover the masked token this way. Compared to the GPT model, the BERT model uses a bidirectional encoding mechanism where all the tokens are encoded bidirectly. It can see the previous information and see the future information. While for the GPT model, it can only see the previous information, well, but not the future information. And the BERT model was proposed in 2018, and it does not stop there. Recently, last year in 2024, because people witnessed so many success in the GPT model, and the transformer used today are not the same as the transformer model proposed in 2017. So the people also adapt the technique in the modern GPT model to a BERT model and train a model called modern BERT. And the differences compared to that in 2018 covers the architecture, implementation, the data, and the contextual lens. For the architecture, in modern BERT, people do not use the bias term, use the ROPE, positional encoding, using pre-normalization, and so on. And for the implementation, they use more advanced implementation, like the flash attention or something more, the module. In terms of the data, the modern BERT is trained on 2 trillion tokens. And for contextual length, the length is significantly increased. And for the performance, model BERT is better than the BERT model. And the BERT model is also good. And we sometimes use BERT model in several cases, like calling GPT is always expensive. So when we have some local tasks, like train a quality predictor or train some NER, named entity recognition model, we still fine-tune some BERT to get results quickly. But according to the main contents publicly, and the BERT model compared to GPT model, it lacks the significant scaling effect and the emergent ability. And the BERT model is good at the understanding task, but for the generation task, BERT model is not as good as the GPT model. So this is a brief mention of the BERT model. Okay, that's the end of the CS part or the AI part. We will now go to the science discovery, stepping from the natural language to scientific discovery. This is the research scope of our scientific discovery, mainly the microscope from electron, molecular, material, drug, protein, and to cell, human, and the population. This is not the overall scope of the scientific discovery. People can also work on the weather forecasting, the atmosphere, or something more. But our scope mainly focuses on the molecular part in this part. So for the molecular part, we have to deal with the sequence, the graph, and the structure. Let's start from this part. For small molecule, for protein, DNA, and the periodic material, fortunately, they all have a sequence representation. For a small molecule, this is aspirin. This is the chemical graph of aspirin. It has a sequence representation like this. We can use depth-first search to convert a graph into a SMILES string. I know that the short name of the summer school is also SMILES. And the sequence representation of the molecule is also called the SMILES. In this way, we can convert each molecule into a 1D representation. And for protein, it also has the sequence representation. It is called the FASTA sequence, using the amino acid, putting the amino acid sequentially. And then we can use this sequence to represent that protein. For DNA, the story is the same. We use the ATGC to represent a DNA sequence. Well, for the inorganic material, and we can using something like the chemical formula plus a space group to represent the material. And this is not a perfect transformation. What the complete means, sorry, it means
encode in smiles. How do you encode in smiles all the different edges between the atoms?
Thank you. If you're specifically talking about the relation between the graph and the smiles, and you care about the edge, we can add the edge into the smiles. You can see that the equation symbol, it is a double bond, and you can it also has the triple bond. Every bond is embedded into the sequence, both the atom and the bond. But it indeed has information loss. It is the 3D information, not encoded in this sequence.
Mm-hmm. Okay.
Thanks. If you care about the bond, doesn't matter. But for the 3D structure, indeed loss. Okay, thanks. So, okay, we can continue. And after this proposal, and I tell you that there are many tasks similar to that in natural language processing, like predicting some property of the small molecule, predicting the property of the protein, DNA, material, and so on. Then we can have many immediate ideas, like apply the pre-training technique from the natural language processing to science discovery. And indeed, there are so many models like this, like the BERT model for the small molecule called CAN-BERTA, EVMP, like the BERT model for the protein, like the ESM, and the GPT model for protein, like the ProGene. And for extreme PGRM, it is more like a combination of the BERT and the GPT. For the DNA model, we have the DNA BERT, the NT. They are the BERT model for the DNA sequence. And we also have the EVO model and EVO2. And EVO is also, EVO is published in Science, and it can handle the super long sequences. The differences in terms of the contextual length for the three modalities. A small molecule, the tokens we use to represent a small molecule usually lie in 30 to 50 tokens. For protein, it is a bit longer, about hundreds of residues. For the DNA, it is longer, usually 100,000 nucleotide for this level. And after pre-training those models, we can immediately use the model for several downstream tasks like the ADMET property prediction for drug discovery, and also for some protein design tasks in the middle part. And we can also use the fine-tune the BERT model on several downstream tasks to predict the solubility or stability of the protein or the function. Similarly for the DNA and RNA cases. And next, I want to tell more about the science discovery or the drug discovery. We can start from a real case. And this is the general pipeline of the drug discovery. We need to first start from the target identification, then compound screening, hit, lead, and wet lab experiment. And for target identification, this means that once we decided to work on some disease, find some new drug for the disease, usually we need to find which proteins in the patient body is related to that disease. We need to find that protein and design some drug for that. So this is the protein discovery phase. This is the target discovery phase. After having the protein, we can design a compound for the given protein. Previously, people using a technique called compound screening, which means that we can using some computational-based software and prepare a compound library. And we estimate the binding affinity between the compound and the target protein, output a value, and rank the candidate compound based on the value. And after finding something promising, we can conduct some initial wet lab experiment to verify whether the compound are bioactive on this protein. And then we gradually optimize the discovery compound. And finally, once everything goes smoothly, we can go to the clinical trial and get approved. So this is usually a very long process, 10 years and $10 billion for a drug. This is a rough estimate. The compound, the chemical space is very, very large. And we can see that currently the largest compound library has 10 to 10 compounds. It is very cost to enumerate all of them. And compared to the whole chemical space, the largest compound library is still small compared to the whole chemical space. The whole chemical space is estimated to have 10 to 60 compounds. So there are so many things we need to explore. Now the question is like this. We have a target protein P, and we want to design a compound ligand that can bind to the protein. And we also want that the discovered ligand is bioactive. So how to solve this problem? Previously, people can use the screening-based method, like finding a compound library and estimate the binding affinity between each compound and the target and select the top one. This is a prediction method. This is a predictive mindset. But now we are in a generative area here, and we see that the whole chemical space is super large. So can we directly generate the compound based on the input of the target protein? And because, as I mentioned, we are the AI researchers, we work on the sequence modeling. So we connect this problem to the machine translation problem. The machine translation is want to translate something from a source language to a targeted one, like translate Russian to Chinese, English to Chinese, and so on. And the model has an encoder and a decoder, where the encoder encodes the language and the decoder outputs the language, the target language. So this is the general framework. It seems that we can apply this work into the drug discovery cases, where we can have a protein targeted encoder encoded into the hidden space and decode a SMILES from the target side. Okay, after getting this idea, we can implement in this way. First, we need to do some preparation to prepare a good compound generator. The reason is that currently, the high quality protein ligand pair is limited. We do not have so many data like that. So pre-train is helpful. We first pre-train a compound generator. It is a GPT-style model trained on 10 miles. And after that, we connect the encoder to the decoder, where the encoder is used to capture the protein information. From this part, the protein is a 3D structure. So we slightly change the transformer to encode the 3D information. And after that, we connect the encoder to the decoder and finish this part. This is a conventional encoder and a decoder framework. And for the encoder, we need to input the 3D information of the protein as well as the protein sequence. But this is not the end of the story, because there are some technical issues. Multiple ligands to bind to the same target, and we see this problem in our database. We need to handle the one versus many mapping cases. And also sometimes we need to generate many diverse drug or diverse compound for this purpose. And in this way, we introduce the variational autoencoder into this part, where the contextual encoder is used to encode the protein as well as the compound, generate a latent distribution from the mu-z and the sigma-z, and sample the noise from this joint distribution and feed the noise into the decoder. So in this way, by sampling different noises, we can get different output from this side. So this is the general framework of the model. We call this model the TAMGEN, target-aware molecular generation. And the training data is about 300,000 pocket ligand pair. And this is the loss function is the next token prediction plus the variational loss. And this is the results part. And we can see that by combining all these techniques together, the Temgene can indeed find something interesting and compared to the baseline method. And an overall metric covering the docking, QED, and so on, the method outperforms the best. And if you work on drug discovery, one important factor is the docking score. So we suppose that the generated compound has higher docking score. But we can, let's see the output of the baseline method, the pocket to mole, restriction, and the targeted diff. We can see that although the pocket to mole, restriction, and targeted diff might have better docking score compared to the Temgene, you can see the first column in the left picture. In terms of the docking score, the Temgene overall ranked the second, while the targeted diff ranked the first. Although the targeted diff has some good docking score, but the output molecule is super complex. Many rings fuse together, and there is a big ring in the molecule. So this is not what we want, because if a molecule is so complex, then it is very hard to synthesize the compound, and it might bring some potential toxicity. So we prefer some simple molecule. From this sense, we can see that the Temgene can output the compounds with reasonable docking score and simple structure. So this is a good case for drug discovery. And this is the real-world application we have made. And for the disease, the TB, we use a target called CLIP-P. This is a well-known target for the TB. And the method designed 16 compounds in total. We synthesized them and found that 14 out of them shows promising bioactivity. So this shows that Temgene is a usable method for compound discovery. And this is a case study where the input is the CLP and a weak compound we have. After inputting both of them into the contextual encoder, we can get this compound. And the IC50 value estimates the binding affinity between the target and the compound. The lower, the better. So we can see that the design compound is about 100 better times improvement compared to the input. And it is very hard to connect them in the chemical space. And a new compound is always welcome because we can apply patent for the new compound. We have many potential optimization opportunity for the new compound and so on. The next thing is about the simple trick of using the sequence model or Temgene model. And now the task is that I do not want to generate a completely new compound. Instead, I already have a fragment, and I only want the model to grow from one motif. Can you do that? And this is very simple. For the previous compound, you can see a yellow circle. I want to further grow from the yellow circle. And the trick is that we first need to rewrite the smiles of that fragment and let the connecting point ending with the smiles. And we feed the prefix into the decoder part and let the decoder continue generation from the start part. Then we can get a fragment. This is also a very useful trick. We can see that after continual generation from this part, and we found a compound whose binding affinity is about 10 times improvement compared to the reference compound. And still, the lower, the better. So this is a very interesting case to use Temgene. Okay, after using Temgene, because we have a GPT-style decoder in the Temgene model, and we want to train a larger model. Before starting model training, we conduct a survey to see the recent progress of using large foundation model in science discovery. We divided them into different domains like the material, small molecule, protein, RNA, DNA, and a single cell. And for the x-axis, it is the time before 2022, 2023, 2024, and 2025. We can have some trend. We can observe some trend of the model. And A smaller circle indicates a smaller model, and a bigger circle indicates a larger model. We can see that generally, people like to train larger model for different science domains. This not only happens in natural language processing, but also in the science discovery. Like you can see that in the protein part, for the AlphaFold 2, the scale is about 100 million parameters. And for ESM, the model is larger. ESM3, 98 billion parameters, and so on. And also, people not only train larger model, but also train cross-domain models. You can see that at the end of the 2024, the AlphaFold 3 model covers multiple domains, including the DNA, RNA, protein, and small molecule. And in 2025, more cross-domain model appears, like the BOS2, LUCA1, and ADIT, and UMA, and so on. They cover different domains, like the BOS2, AlphaFold, and LUCA. They cover the biological domains, small molecule, protein, DNA, and RNA. And for some model, they cover the small molecule and the material domain, because we have some organic material and inorganic material. But people just realize the trend that we need to train a cross-domain model. We need to train a general purpose model. And we also want to dig into this direction. By witnessing the success of the Generative Foundation model and survey the recent trend, we train a GPT-style science model in this way. And let's see this chart. And as we introduced in the beginning, many science entities can be converted into the sequence representation, like the small molecule, protein, DNA, material, and text. So, okay, let's just collect a lot of data and put them into the model to see what happens. But is that everything? The answer is no. Because if we simply putting all the data from different domains together, it is hard to connect them. We cannot connect small molecule to protein, cannot connect protein to DNA, and so on. And the second thing is that we want to inject the text into the model, because we hope that in some day people can chat with the model to obtain the knowledge they want. And we have many well-known large language models, and we want to inherit the language ability. So how to avoid that the model forget the text ability of the model? These are two problems we need to solve. And for the cross-domain data, we want to systematically handle this case. And we can see that the cross-domain data can be connected in three ways: the physical laws, the science literature, and the biological principles. For the science literature, we will give some detailed example later. First, let's see a paper of a scientific paper. And this is the paper of the in silico medicine using the AI technique to discover the drug. And now the drug is in clinical trial, phase 2. And let's see the abstract of this paper. The drug name, rentuximab, and the target name, TNIK, are both mentioned. But currently in this abstract, they are represented by the natural language. And we can first using some NER, the name, the entity recognition method, to detect the name and convert them into the corresponding format.